So a slight change of emphasis then. Just going to start looking at what are the technology developments about and how we are using them for in situ monitoring. So just to set the scene a little bit for you, what are the existing and emerging platforms and technologies out there? So let's look at the platforms first. So going around in sort of clockwise from the Argo floats. The Argo network has been around since around about 2000, and what the Argo network is about 3,500 floats out there that sit at about 1,000 meters down and then profile through the water column, doing that every 10 days or so. And then moving around, we've got gliders that carry various sensors. The glider technology has been around since about 1960, but it's actually only recently, because of increases in electronic technology or improvements in electronic technology, we've been able to use these platforms in a widespread way. Wind farms, hopefully we'll be able to start using wind farms, all these offshore wind farm developments, in mounting novel instrumentation packages and devices. For example, we only go out to sea really when the conditions are fairly benign. We don't go out and sample when there's a hurricane blowing, for example, and that's when that's where we really need to measure to pin down things like air-sea exchange of gases. Buoys have been around since the 1960s, or our American friends like to call them buoys. Actually, it's a much better way because it overcomes any problems of misinterpretation. Buoys have been around since the 1960s, but again, because of improvements in electronics, we've only been able to use them in a more widespread way since really probably the last 10 or 20 years. Cable observatories, I'm going to talk a bit more about that in a moment, but there's a picture of the wave hub down there, the cable to the wave hub. We've been able to use that to test out instrumentation. And then finally, ships. We've been able to use ships really since man's been able to build them, which is about 50,000 years before present. That's not, the caption at the top of that doesn't mean to say that the RS Discovery has been around since 50,000 years before present, although sometimes sailing on her you think that it possibly has been. So that's about the in situ measurements. It's also worth mentioning what we can measure from space using satellite technologies. So just again, moving around in a clockwise direction, we can measure the sea surface height from space, and we've been able to do that since about 1992. We can also measure, this is a very new development, the sea surface salinity since about 2010, and these are all on a global scale. Then moving around again, we've ocean colour sporadically since about 1978, but actually in a more robust and operational footing since about 1997. And then finally, sea surface temperature. The technology is very well proven there since about 1979. It's very important to note, though, whenever we look at satellite pictures, we think that we've got the global ocean nailed because we've got a global picture. In actual fact, what we're looking at is the top surface layer of the ocean. So for sea surface temperature, we're looking at the skin temperature of the oceans, whereas when we're looking at ocean colour, we're a little bit more lucky because of the optical frequencies. You're actually looking at the top 10 metres of the water column. So what are the existing technologies then as opposed to platforms? Flow cytometry is an idea that has been borrowed from the medical sphere to size sort plankton. So what are the directions of travel for flow cytometry? So there's a very small picture there of a flow cytometer, but basically it's a very large instrument that fills up half your laboratory. So what are we trying to do? We're trying to make these technologies much smaller. So we're going for lab on a chip towards a lab on a chip type approach. Again, nutrient analyzers, they're very large, but we're trying to use and develop microfluidic technologies, so going to very much smaller scales. And then looking at plankton nets, I don't think we'll ever get rid of the idea of the plankton net, but what we're able to do now is to go towards much higher throughput technologies so that we can identify species much more quickly, and harmful algal blooms, for example, much more quickly using genetic techniques. That's what the diagram on the bottom is showing. So what is the current landscape for technological development? Well, I think it's actually full of factoids, mantras, and challenges. I'll unpackage that a little bit more. I think it's a jumbled assemblage in actual fact. So my particular favourite factoid is that we know more about the surface of the moon than we do about the oceans. Depends who you speak to about how this particular factoid comes out, but it sometimes talks about the deep ocean or the ocean in general. And then we've got all these things about our measurements. We've got large instruments that we have to take to see that really, if we're going to measure the global ocean properly, we need to make them much, much smaller. Data sparsity. The oceans are chronically undersampled. I think that's a given. I don't think anyone here would disagree with me on that. And then I want to pick up on this, this mantra that was coined a few years ago: faster, better, cheaper. So what are the challenges? Well, in actual fact, we're actually only measuring a fraction of the needed parameters for measuring biogeochemical parameters and physical flows. We actually lack basic understanding of fundamental biogeochemical processes. And as I've already said, the oceans are data sparse in space and time. So how do we move from this cold, grey world of science fiction into the bright yellow world of science fact? Or, as I'd like to rephrase that, how can we move from the cutting edge to the operational? And the cutting edge is really summed up by things being very expensive, they're very limited, and they're very bespoke. So you build a piece of equipment that you take to sea, and there's one of a kind. What we need to move towards are things that are much cheaper, things that measure lots of parameters, so they're general in nature, and also we need to move towards ubiquity so that these instruments can be deployed anywhere in the global ocean. And there isn't a nice straight linear line that joins these two spheres. I actually like to see that you have to pass through something I've called the cone of pragmatism. So what is the cone of pragmatism? Well, basically, it's this pinch point that you have to go through between going from cutting edge to operational. And that pinch point is that, or that cone is actually pinched by these nasties: cost, power, in terms of, I mean, electronic power. I don't mean power as in political power. Bandwidth, so the amount of information that you can easily get from those instruments, and also data processing. We need to be able to process data from these things, all these instruments, very, very quickly. So I'd like to use a case study. Unashamedly, this is going to be a plug for a cabled observatory that we've recently launched off the coast of France. So get to that in a moment. So faster, better, cheaper. That's the mantra I want to pick up on and really ask the question. The faster, better, cheaper mantra was really personified by Dan Golden in the early 90s. He was the longest-serving administrator of NASA, and this was really a mantra that he, or philosophy and policy that he espoused in NASA in the early 90s. It's come under for a lot of criticism, possibly rightly, but actually, if you look at the number of missions that he successfully fronted up, it was a very successful mantra. So let's look at cabled observatories. Arguably, cabled observatories are slower, possibly better, and certainly not cheaper. But stay with me for a moment. There are several examples around the globe of these cabled observatories at the moment. There's Mars in the US, there's Venus in Canada, there's Neptune in Canada. Now, you don't have to call your cabled observatory one of the planets of the solar system, I hasten to add, but it seems to be a trend. And then there are other ones. But generally, these cabled observatories tend to be in regions of tectonic activity. So that gives you the economic driver behind putting in these extremely expensive cabled observatory networks. So, for example, if we want to know what the San Andreas Fault is doing, for example, it's very useful to know with these cabled observatories. What the oceanographic community has done in the States is that it's piggybacked a lot of its instrumentation and a lot of its instrument development on the back of these networks. But where these cabled observatories are excellent is that they are excellent for flexible experimentation. You've got limitless power and you've got limitless communications, so that almost the unthinkable is that you can put your instrument in the field and you can interact with it and you can reprogram it, so reschedule it and things like that. So it's excellent for that. And as I've already said, for instrument development. So here's the shameless plug for what we've recently done off the coast of France. So you're sat just where it says L4, well, just inshore from where it says L4 Buoy. Otherwise, it's on the beach out there at the moment. The cabled observatory we've launched is just off the west coast of France on an island called La Molène. And this is something we've done with Ifremer and a few other partners in an Interreg project that we've had going. This is the world's first dynamic coastal observatory. We launched it in June. And the sorts of things that we're able to measure with this cabled observatory are acoustics. So if you'd like to listen to the cetaceans and the shellfish, you can actually go online and listen to them. We've got HD cameras down there. We can measure all the environmental parameters that you wish for, and those are in very high frequency time frames. Again, as I've already said, these data are programmable. We've got high data rates, and also, uniquely, we can process these data in very short order. And if you'd like to have a little bit more information, there's the website there. So back to Dan and his mantra of faster, better, cheaper. I'd actually like to make it even more difficult for us. We actually need to go faster, better, cheaper, and smaller. So is there any scope for getting the obvious benefits of cabled observatories through this cone of pragmatism? And I was very pleased that Wendy picked up on this yesterday. There is an alternative to having these very high-cost cabled observatories, is that we can use this existing submarine cabled network. And this isn't a new idea, or it's a relatively new idea. It's not an idea that we've had, but there is a report by the International Telecommunications Union and the World Meteorological Organization, who have espoused the use of these telecoms cables. Now, if you look at the distribution of where these telecoms cables are, some of it is pretty fortuitous, actually. There's a line which runs right across from the Canaries to the US, for example, exactly where the rapid array is. So why don't we just get our thinking caps on to go faster, better, cheaper, and smaller to get instrumentation on these submarine cables? Again, there's another one up north from Norway up to Spitsbergen, which again, that's a very important area of the global ocean. So, translating science fiction into science fact, I think we should use, and this is a very specific example, we could talk all day about all the various different platforms that I introduced at the start, but I think there's an opportunity to use the cutting edge of the cabled observatories as R&D platforms to pull through into operational use on this existing telecommunications network. We obviously need additional work on the miniaturization of these instruments, and there will also be very large limits placed on power requirements and data rates by using this submarine network. But I do believe that this will result in a myriad of depth profiles. Remember, satellite data is very limited to the surface. Once we start getting a handle on what is going on in the ocean interior, that's going to allow us to really say that we're properly observing the global ocean. And if we've got these depth profile measurements, we will then properly start to resolve these global biogeochemical flows and processes. So thank you very much indeed.